Hi, how are you? And for this exercise, we're going to be going over Chapter 11's 11.5 exercise. And this is from the book Introducing the Theory of Computation by Wayne Goddard. So the problem is as follows. We are to draw a TM that accepts a to 0 to the a power, 1 to the b power, such that a is less than b. And those a and b values can just be the counts of zeros and ones. So a is the count for zeros and b is the count for ones. That's all that means. So when thinking about this Turing machine that accepts this certain language, it's always good to be able to visualize it, and that's exactly what we're going to try to do here. So before we look at the code, let's get a quick visualization of the theoretical Turing machine that this would create for us. And this is the Turing machine right here. And we can test a few inputs just to see how it actually works and how it accepts stuff and rejects stuff. And right here, I already preloaded some values. And if we run it, we see what it accepts and rejects. And this can be any shape, size. There's many ways to do this, but the general, I guess, topological structure will be mostly the same. It won't change too much. So let's get into the nitty-gritty of what is actually happening inside the Turing machine. We could look at the transitions and arrows, but I think a fun way to look at this is also the program behind it and how it'll work. Now, this is Python written, and this is a Turing machine kind of program that only works for this specific Turing machine. So what that means is it's not a general program for most Turing machines, it's just catered to this one. And that's done on purpose. This is also not the most efficient way of doing this, but it's done just to help show what's happening on the inside and kind of help paint a picture of why this is happening this way. So when we first want to test our strings or inputs, whatever we're trying to pass into our Turing machine, we imagine this function as our Turing machine. So the first thing is we have a count for A and B. So this is going to count our ones, this is going to count our twos. And what happens in here is, as long as our language, so first things first is we can't accept anything that is a 1 in the first position because the language is 0 to the a power, 1 to the b power. So it has to start with a 0. So we know that if the language is a 1, if the first piece of the string is a 1, or the first piece of the input is a 1, it's going to return false. Same thing if it's nothing. If we have nothing in there, that means that A is equal to B because we both are nothing, right? So that also is going to return false. I just put this in here just to cover my butt twice. This is actually handled in the program itself. You kind of don't need this part, but just to help visualize it a little better. So then we go on to the actual piece of thinking behind the algorithm. So we know that we can have as many zeros as we want, right? As long as we keep track of them with our a variable right here. So we're going to parse through all the zeros that we have, and we'll stop only when there's no more zeros to read. So what this says is, as long as our string, our input, isn't empty, and there's more zeros, and there's a 0 at that current index, we're going to count an a value, and then we're going to shrink down the string or the input so that that current value is just removed from the string, just to stop any overlaps from happening or any errors like that. This way we can just keep track of what's still in the string or still in the input. And once that's done, we can parse through all of our ones. And this is keeping count using B. So to keep count of all of our ones, we'll do the same thing just like for zeros. As long as it's not empty, and as long as at the current index it's a 1. And then we'll start the count with all our b's, and then we'll shrink it down so that it removes that current element in the tape or list in this case. And so once that's done, if there's anything left over, so let's say we have an example of 0, 1, 0, just to give something out there. If you give it 0, 1, 0, what will happen first is it will check to see if it's empty, it's not empty, check to see if the first index is 1, it's not 1, so this will be passed through, and then we'll go on to the next piece of Boolean logic that we have to hit, and which is the while loop, and we'll check to see if both these clauses are true, and they are the language or string, our input is not empty, and the first index is 0, so we're going to keep track of that, and then we're going to shrink it down. So now our language or our input will be 1, 0 instead of being our previous original 0, 1, 0. And now after that, we go on to read in all of our ones, and we notice that we have 1, 1, so this will be 1 for B, and the language will be reduced to just being a 0. And notice how that 0 is going to be left in the input string. So we're doing nothing with it. It's being left in there. And typically what should happen is if anything is left over, or if it hasn't been read by the Turing machine, it should be rejected. In this case, we're not handling it that way. What we're doing is we're trying to make sure that the actual requirements for the Turing machine are met. So now that we have our 0, 1, we're going to see if it's acceptable. And since we have the same amount of zeros and ones, so that means A is equal to B, it's going to return false. And we can see that when we run it, it returns false for us right here. So now, I guess the question would be to ask is, what if you have, let's say, 2 zeros, a 1, and a 0, and it'll still return false. So pretty much anything that doesn't, so as long as this 0 is here, it'll keep throwing it off. That needs to be removed. Once that's removed, it will accept, because being left in the tape or the list, so the Turing machine will count that as a incomplete input or not a valid input. And that's it. All right. Thanks, guys.